All right, let's just dive right in. Welcome back to The Explainer. Today we're unraveling a pretty wild cosmic detective story. You know, we often picture astronomers just peering through telescopes and immediately shouting, "Eureka!" But honestly, it's way more like a high-stakes forensic investigation. We're going to look at exactly how these scientific detectives actually decode the secrets of the night sky step by step, using a very specific celestial crime scene. To get to that crime scene, imagine zooming about 500 light-years away from Earth. Now, 500 light-years might sound kind of close in galactic terms, but we're still talking roughly 3,000 trillion miles. It's far enough out there that piecing together its exact history takes some serious ingenuity. And that journey drops us right at our subject for today, Caldwell 85, or as you probably know it, the Omicron Velorum open star cluster. It's located right there in the Vela constellation. This beautiful grouping of stars basically acts as an active, deep space laboratory for us. By studying this exact cluster, we get this incredibly controlled environment to figure out exactly how stars are born, how they age, and how they behave over millions of years. But here is the real hook and the core of our explainer today. There was a massive discrepancy here. For decades, the scientific community had the age of this cluster completely wrong, like off by 20 million years wrong. So today, we're going to crack that case and look at the exact evidence researchers used to rewrite the history books.
Part 1. Meet the Omicron Velorum cluster.
So, like I mentioned, this cluster sits in the Velas constellation, and it's the universe's ultimate lab. Why? Well, it has 66 confirmed stellar members, meaning these 66 stars are physically moving together through space as a confirmed group, and they all formed from the exact same molecular cloud at roughly the exact same time. The brightest star anchoring the whole thing is Omicron Velorum itself. The cluster even features some really complex dynamics, like the quadruple star system HD 74438. Because these stars were all born together, it's pretty much the perfect baseline for testing our theories on stellar evolution.
Part 2. Finding the true cluster members.
Now, before we can determine anything about the cluster's history, we hit a major forensic hurdle. How do we actually prove which stars belong to the cluster and which are just, photobombing background stars? You can't just assume every speck of light in that patch of sky is a member. So scientists run their suspects through 4 rigorous steps. First, check the proper motions. How are the stars moving across the sky? Second, radial velocities. How fast are they moving toward or away from us? Third, look for specific chemical behaviors, like H-alpha emissions, which are those glowing hydrogen signatures typical of rowdy young stars. And finally, step 4, analyze the gravity dependence of sodium. And this completely nails that 4th step. By measuring specific properties of sodium against a star's color and temperature, astronomers can easily separate the true younger cluster members, which you can see as those open circles, from the older field star imposters, the solid dots. Those older background giants have a totally different surface gravity than our young cluster dwarfs. So this measurement literally catches them in the act, letting us kick the imposters out of our dataset for good.
Part 3. The stellar age mystery.
Okay, so we've got a solid, verified list of suspects. Now we hit the core mystery of the explainer. How old is Caldwell 85? For years, astronomers used traditional models to date it. They looked at the most massive stars to see when they started exhausting their fuel, when they moved out of that normal adult life phase known as the main sequence turnoff. Doing that, they got an age of roughly 35 million years. But then, a newer method came along and pointed to an age of 50 to 53 million years. That is a massive contradiction. Naturally, it sparked this intense scientific debate because the models were completely clashing.
Part 4. Tracing the lithium boundary.
To settle the dispute, astronomers couldn't just guess. They needed a smoking gun. So they turned to something called the Lithium Depletion Boundary, or LDB. Think of this as a cosmic ticking clock. Young, low-mass stars are born with a specific amount of lithium. As they contract and their cores heat up, they eventually hit a temperature where all that lithium gets destroyed. If you can find the exact mass at which stars in a cluster still have lithium versus the ones that have burned it all up, you can calculate a highly precise age for the entire cluster.
Let's look at how this plays out in practice. Zooming way into a microscopic scale, researchers are hunting for a tiny dip at a very specific wavelength, the exact chemical signature of lithium. Check out the dotted vertical lines marking this zone across the spectrum of 3 candidate stars. That top star, CTIO-038, it has a clear dip. It still has its lithium.
But the bottom star, PP14, which is just a tiny bit brighter and more massive, its lithium is completely gone.
So they take all those spectral readings, plot them out, and boom, they find the exact boundary line at a magnitude of 16.2. Above this line, 0 lithium. Below it, lithium is detected. By plugging that exact boundary into their theoretical models, they definitively proved the cluster's true age is actually around 50 to 53 million years old. The decades-old era was finally solved.
And hey, this wasn't just a fluke for Caldwell 85. When we compare Caldwell 85's lithium boundary to other famous clusters like Alpha Persei and the Pleiades, the exact same dating method works consistently across the board. It turns out that older turnoff method was wrong because the models for high-mass stars were missing a crucial physics detail about how energy aggressively mixes inside their cores. The lithium clock and the lowest mass stars basically cut right through that confusion and revealed the truth.
Part 5. Spinners and Brown Dwarfs.
The really cool thing here is that pinning down that true age of 50 million years suddenly helped us decipher other clues about stellar behavior that we just couldn't make sense of before. For instance, astronomers noticed this wild split in how fast these cluster members rotate. They basically fall into two distinct groups. Some are incredibly slow, but then there are these extreme outliers whipping around at almost 240 kilometers per second. I mean, look at star 4658. It's spinning at a blistering 238 kilometers per second. Because we now know the cluster is exactly 50 million years old, scientists can use these varying spin rates to map exactly how young stars lose their angular momentum and slow down as they age.
Plus, because we finally know exactly where to look and what to look for, we're using this deep space lab to hunt for the universe's most elusive objects, brown dwarfs. These are objects that failed to accumulate enough mass to ever ignite sustained nuclear fusion. By pushing our instruments to the absolute limit, astronomers successfully identified objects like CTIO 160 sitting right at the substellar limit. It gives us this incredible, true snapshot of early star formation.
And this final piece of evidence visualizes that perfectly. It shows the cluster's main sequence extending far, far deeper than anyone originally thought. All those dots trailing off toward the bottom right, those are our pre-main sequence stars and brown dwarfs. It proves that when we use the right forensic tools, like proper motion tracking and lithium depletion, we can uncover a massive wealth of young stellar objects that were literally hiding right there in plain sight.
So, we've tracked the clues, separated the imposters, corrected a 20 million year error, and discovered ultra-fast spinners and failed stars? But it really makes you wonder, right? If a relatively close star cluster, just 500 light-years away in the Vela constellation, can hide this many incredible secrets and force us to completely rewrite our models of how stars age, what else is out there, right now, just waiting for the right cosmic detective to come along and discover it? Thanks for exploring Caldwell 85 with me today on The Explainer, and keep looking up.